Greetings. This video covers material in Chapter 7, which is part of structural analysis. Again, we're finding internal forces in members. The material today differs from what we've done earlier with trusses in that these members that we'll look at today are not two-force members, so they can have more than just tension or compression forces. So for example, here is a cantilever beam that has a fixed support at A and two applied loads, P1 and P2. And we want to find the internal forces at point B. And it's important to know the internal forces so that we can properly design the member, that is, sizing and material. So what we do is we will use the method of sections, much like we did for trusses, finding internal forces in trusses. We can use the method of sections here, where the forces that were previously internal forces become external forces, and we find the conditions of equilibrium on a section of the member, and that will give us the internal forces. There are three internal reactions that we look for. We have a normal force, which is tension or compression. So that acts, you see the line AA, the blue line. The normal force acts perpendicular or normal to that line. There's also the shear force, which acts parallel to line AA, or your section line. And then there's a bending moment. So here is a section of that beam where we've divided it along the blue line, AA. And now we have a portion on the left half from A to B, and then a portion from B to the end. And so here are free body diagrams for those two sections. You see on the left we have the beam from A to B, and we have the reactions at the wall from the fixed support. So this support here provides reactions, and those are shown in the diagram. And then here are the internal forces. Well, they were internal to the entire beam, but for this section they're now external forces. So we have the normal force here, the shear force, and the bending moment. And then on the other section of the beam from B to the end, we have the same internal forces, just with opposite sense. So the normal force, shear force, and bending moment. And we got to make sure to keep all the external forces. So here we have the applied loads, and here we have the reaction forces from the support. Now there are certain sign conventions when working with these internal loadings, and they are as follows. For the normal force, tension is positive. And you can see that the normal forces for both these sections are shown as positive. So it's good to just draw them in their positive sense. For shear force, which is denoted V, the convention is that the shear force causes a clockwise rotation. So that's kind of confusing from what we worked with before with bending moments, but anyway, that's how it is. The convention is that clockwise rotation is positive. And for the bending moment, positive bending moment causes the member to bend concave upward. That is, it sort of makes a smiley face. So here are the three internal loadings, and they're shown in their positive conventions. So normal force is positive in tension. Shear force is positive if it causes a clockwise rotation. And the bending moment is positive if it makes the member want to form a smiley face. So if you think of grabbing each end of this section here and applying a moment, like twisting it in those directions, it would bend down and make sort of a smiley face. And you can see that it's shaded in light gray as being concave up. So again, we just have two simple steps to find the internal loadings. One, we separate the member by drawing a perpendicular line, so a line perpendicular to the main axis. And then we draw the free body diagram. And be sure to take care with any distributed loads. For example, if there's a beam that has a distributed loading on it, and you want to find the internal forces at this point, when you draw your new section, you have to include the distributed loading that's on that section. So you have to include this. And it just has a height, whatever the height is right here where you cut it. And then once we have a free body diagram, we apply the equations of equilibrium. So we have this rigid body, we apply the equations of equilibrium. How many equations are there? For a rigid body in 2D, there are 3 equations of equilibrium. Let's look at an example. This is example 7.2 from the book, and we'll just walk through it quickly. The question is, find the normal force, shear force, and bending moment at C. So imagine a vertical line passing through the beam at C. We'll go ahead and draw the free body diagram of the section we're concerned about. And I'll draw the section from C to B, because that way we don't have to find the reactions at A. So here's C, and B, and the distributed load. Let's see, its height at A is 1200 newtons per meter, and then it decreases linearly to the end. Since C is halfway between A and B, the height here is 600 newtons per meter. And then we need to draw the internal loadings. So we have the normal force, draw it positive. We have the shear force, draw it positive, and a bending moment, and it's drawn positive. So we have tension, clockwise rotation, and concave upward. So perhaps I should have, okay, now I'll just redraw it as the equivalent force from the distributed load. First, let me draw the internal loadings. There's V, N, and M. And then here's the equivalent force from the distributed loading. It has a magnitude of this area of this triangle, so that's 1/2 times 1.5 times 600 equals 450. And it acts at a distance 0.5 meters from point C. Alright, so now to find the internal forces, now that we have our free body diagram completed, we will just apply the equations of equilibrium. So I'll start with moments about point C. We have negative 450 times 0.5. And then m is shown as a negative moment because it rotates in a counterclockwise direction. Because when we talk about, now that we're talking about this Cartesian coordinate system, we're talking about moments in the z direction. So we're not talking about internal forces as far as the positive and negative. We're talking about in the z direction. So m is negative, it's in the negative z direction. And so those add up to 0, and we get that m is negative 225 Newton meters. Okay. Forces in the y direction, we have v and then negative 450, and those add up to 0, so v is 450 newtons. And forces in the x direction, the only one is the normal force, so n is 0. Okay. So now just walk through a couple more examples. Again, we're finding these internal forces by splitting the member into a section and treating the internal forces now as external forces. And so we know that that section of the member is in equilibrium, so we find the forces that keep it in equilibrium. And here's just the better drawings of that problem. Okay, so here is fundamental problem 7.5. And again, we want to find the internal loadings at point C. So for this problem, because we can't make a section without some external, without the reaction forces, either at A or B, we'll go ahead and we'll have to solve for those first. So fundamental problem 7.5. So the free body diagram of the entire beam. We have a force at B, two forces at A, two reactions at A, and then the distributed load, I'll treat it as two separate forces. So this one acts at 2 meters. Anyway, they both have magnitude 1/2 of 3 times 9, so that's 13.5. And this one acts at 2 meters from A, and this one is at 4 meters. So we can get FB with the equation sum of the moments about point A. So we have negative 13.5 times 2, negative 13.5 times 4, and plus FB times 6. And that equals 0. So we get FB is equal to 13.5. So now we can go ahead and draw our section. Here's point C. We have only half of the distributed loading on this section, so we have this triangle over here. And so I'll draw that as, I'll go ahead and draw the equivalent system, 13.5 kilonewtons, and it's 1 meter from point C. And then here's 13.5 kilonewtons from B, and then we have the normal force, we have the shear force, and we have bending moment. Alright, now it's just an application of our 3 equations of equilibrium. sum of the forces in the x is equal to negative n, and that's equal to 0. Sum of the forces in the y is equal to v, negative 13.5, and positive 13.5. That adds up to 0, so v is also equal to 0. And sum of the moments about c is 13.5 times 3 from the force at B, minus 13.5 times 1 from the distributed loading, minus m, and that's equal to 0. So m is equal to 13.5 times 2, which is 27 kilonewtons times meters. So the main work is drawing the free body diagram appropriately, and then all that's left is to apply the equations of equilibrium. Another example that we'll look at is problem 717. So here we want to find the force at, or the internal loadings at E. And I like this problem because it sort of ties in what we looked at in the previous chapter with structural analysis for mechanisms. Because if we were to draw the free body diagram of CB, then, well, no matter how we cut CB, or no matter which section we use for CB. So here's CB, and we want to slice it here at point E. So we've got CX, CY, and then well, we would have BX and BY, but here's E, or here's CB, and we know that FC is on the line from C to B, because CB is a two-force member, so there's FB and there's FC, and they're equal, so I could just call them both F, well anyway, I'll call it FC. No, I'll be clear and call them both FB, because they have to be equal and opposite, because those are the only forces acting on member CB. Point E, there are no forces there, we just want to find the internal loadings. So my point is that when we cut this object at E, for both sections we'd have to find FB. So that's an unknown force. So we need to go up and draw the free body diagram for AB first in order to find this FB. And then we can come back and find the internal forces at E. So here's the free body diagram for member AB. We've got AX, AY. I'll go ahead and draw the equivalent force. So that's the area for that triangle is 1/2 times 6 times 400, so that's 1200. 1200 newtons, and it acts at 4 meters. And then here's FB, and just by inspection it needs to be pointing sort of up, but we also know its direction. So its direction is 2.5 horizontal and 2.5 vertical and 6 horizontal. Well, that's really equivalent to a 12, 5, 13 triangle. Just multiply these by 2 and it's a similar triangle. So that gives us the components of FB. So there's our free body diagram that allows us to get FB. Sum of the moments about A will give us the magnitude of FB. So we have negative 1200 times 2/3 of 6, which is 4. plus 5/12 FB times 6. And that adds up to 0, so we get that FB is 2,080 newtons. And now we can draw, now we know FB, and so we can go ahead and draw our section. This is point E, and we have 2080 newtons acting at point B, and then normal force, shear force, bending moment. Okay. And this is a 5, 12, 13 triangle. Okay, so there's our free body diagram that we're working with. And we just have to apply the equations of equilibrium to find these three unknown loadings. The forces in the y direction, we have V, and we have negative 2080 times 5/13. Those add up to 0, so V is 800. The forces in the x, we have negative n, and we have negative 2080 times 12/13. Those add up to 0, so n is negative 1920. So now we have a convention that we adhere to where a positive normal force means tension. So we have a negative normal force, that means that this is in compression. And some of the moments about E, we could have also done it about B, but I'm just going to stick with the way we usually do it. Some of the moments about E, let's see, the x component of FB generates a positive moment about E, and so that is, x component is 12/13 of 2080, and its moment arm, or perpendicular distance, is 2.5 meters. And then the y component generates a negative moment about E, so we have minus 5/13 times 2080, and its moment arm is 6 meters. And then we also have m, which is in the negative z direction. So that all adds up to 0, and we get that m is 2,400 newton meters. So again, the bulk of the work is knowing how to generate or create the free body diagram. We have, in order to find the internal forces, we have to know all the external forces. And so sometimes, like for this problem, we'll have to look at the entire member and then get the external forces. Then we just cut the member at the point where we want to find the internal forces, draw the free body diagram, including those internal forces now, and use the equations of equilibrium to find these internal forces.